Hey everyone, welcome to This Explainer. Today, we're taking the foundational concepts of chemistry, stuff that usually feels pretty dry or abstract, and turning them into a journey that actually makes sense, especially if you're a student trying to wrap your head around this. Let's get right into it.
Nobel laureate Roald Hoffmann really hit the nail on the head with this quote. He reminds us that chemistry isn't just about 100 or so isolated elements sitting on a poster in a classroom. No, it's about the infinite, beautiful variety of molecules you can build from them. It's literally the ultimate study of transformation.
So, here's our roadmap for today's explainer. We're hitting the roots of chemistry, the nature of matter, how we measure our world, the laws of chemical combination, and finally, the math of chemistry. Let's dive in.
All right, Section 1. The roots of chemistry. And spoiler alert, it is way older than you think. When we hear the word chemistry, we usually picture sterile, modern labs and white coats, right? But looking at this timeline, it's pretty clear humans have been master chemists for millennia. We aren't just talking about abstract theories here. It's hands-on applied science. I mean, we're talking about crafting glass objects over 3,000 years ago in South India, tanning leather and dyeing cotton way back in the Rig Veda, even mass-producing plant oil soaps by the 18th century. Our ancestors were actively manipulating matter to upgrade their daily lives. But here's what's truly mind-blowing. Alongside all that practical craft, there was this massive philosophical leap. Around 600 BCE, an Indian philosopher named Acharya Kanda actually conceptualized the fundamental building blocks of reality. He called them paramonu, these tiny, indestructible, indivisible particles that group together to form absolutely everything. Think about that for a second. He was talking about atomic theory roughly 2,500 years before John Dalton proposed it in the West. Absolutely incredible. Moving right along to Section 2, the nature of matter, basically categorizing all the physical stuff around us. So how do modern chemists actually organize all the stuff that takes up space and has mass? Well, we split how we observe matter into two camps, physical properties and chemical properties. It's like this. A physical property is like checking out a car's paint job or weighing it. You're observing it without fundamentally changing what the substance actually is. But a chemical property, that's figuring out how the car's fuel burns inside the engine. To see it, you literally have to trigger a chemical change, like combustibility or reacting with an acid. And when we categorize pure substances based on those properties, we use a pretty strict system. Elements are your absolute pure ingredients. Think sodium, copper, or oxygen. They're made of just one type of atom. Compounds, on the flip side, are the highly specific recipes made from those ingredients, like water or carbon dioxide. They take different elements and lock them together in a strict, fixed ratio. Which brings us to one of my absolute favorite everyday examples. Hydrogen is a gas that burns with a distinct pop, and oxygen literally fuels fires, so you'd logically think combining them would create a massive explosion, right? But when they bond in that fixed ratio to form H2O, water, you get a fire extinguisher. It's wild. The properties of a compound can be entirely, astonishingly different from the elements that actually make it up. Okay, Section 3, measuring our world. This is where we handled the insanely large and the impossibly small. To study atoms and molecules, chemists have to pull off some serious mathematical acrobatics. Why? Because they deal with extremes. Imagine sitting in a chemistry exam and having to write out 0.000, well, you get the idea, 166 grams. That staggering number is the mass of a single solitary hydrogen atom. Nobody has time to write that many zeros during a test, much less actually calculate with it. It's just a nightmare. Thankfully, we've got scientific notation. It is such an elegant solution. It compresses all those zeros into a clean, workable format. 1.66 times 10 to the negative 24th power. By using exponents, we can easily write, share, and do the math on numbers that would otherwise be literally impossible to manage. All right, up next is Section 4, Laws of Chemical Combination. These are the invisible rules of nature. Now that we know how to measure matter accurately, we need to look at the strict, unbending laws that dictate exactly how elements are allowed to interact and combine. When you first look at this list of 5 laws, I know, it feels a bit intimidating. But don't stress about memorizing names right now. Just think of these 5 laws as the fundamental legal system for the microscopic world. They're basically the rules of the road for how atoms reorganize themselves. Let's zoom in on a couple of them.
Check out this actual historical data from Joseph Proust, which perfectly illustrates the law of definite proportions. He took cupric carbonate that he found in nature and cupric carbonate he synthesized in a lab. Look closely at the percentages. They are completely identical. 51.35% copper, 9.74% carbon, 38.91% oxygen. The big takeaway here? A specific compound is always going to have the exact same proportion of elements by weight, no matter where it came from. Nature's rules are incredibly strict.
And that leads us to the ultimate golden rule of chemistry, formulated by Antoine Lavoisier in 1789, the law of conservation of mass. Simply put, matter can neither be created nor destroyed. It only changes form. Whatever mass you start a chemical reaction with, you absolutely, without exception, must finish with. The universal scales have to balance every single time.
Which brings us to our final section, Section 5, the math of chemistry. Time to balance the scales. This whole concept of balancing brings us right to stoichiometry. Now, you'll hear this term a lot in class, but honestly, it's just a fancy scientific word for the quantitative math we use to balance chemical reactions and respect Lavoisier's golden rule. The easiest trick here is to treat a chemical equation exactly like a sentence. The reactants on the left are your before state, the products on the right are your after state, and that arrow in the middle, that's your verb. It's the action of transformation. Like here, 1 molecule of methane plus 2 molecules of oxygen transforms into carbon dioxide and water.
So let's actually do the math together. Take the combustion of propane. We don't just guess, it's a step-by-step process. First, write the unbalanced formula. Then, systematically balance the carbons by popping a 3 in front of the CO2. Next, balance the hydrogens by putting a 4 in front of the water. Finally, balance the oxygen with a 5 in front of the O2 on the reactant side. Step 5 is just our quick verification. Count them up. 3 carbons, 8 hydrogens, 10 oxygens on both sides. The scale is perfectly balanced. No mass created, no mass destroyed. But in the real world, reactions have practical limits. Think about it like baking a cake. If you have infinite flour and infinite eggs, but only 1 cup of sugar, well, you're only making 1 cake. Once the sugar's gone, the baking stops. In chemistry, that bottleneck is called your limiting reactant. It's the reactant that gets consumed first, which completely stops the reaction and dictates exactly how much product you can actually make. Finally, since most lab reactions happen in liquids rather than just swirling around dry powders or gases, we need a solid way to measure concentration. Enter molarity. It tells us exactly how packed a 1-liter solution is with our active chemical ingredients, our moles of solute. It's a super precise way to know exactly how strong your chemical recipe is before you start mixing things together. Well, we've covered a ton of ground today, from ancient Indian glassmaking all the way to calculating molarity and finding limiting reagents. As you wrap up this explainer and head into your next study session, I want to leave you with one thought. Look around your room right now. Knowing that absolutely everything around you is governed by these strict, invisible rules, what chemical reactions are actively shaping your world at this exact second? Keep asking questions, keep balancing those equations, and I'll catch you in the next explainer.